Good morning to all of you. In previous session, we have seen pole location and time domain behavior for causal signal. Depending on the pole location, if it is inside the unit circle, we have classified it as a decaying signal. Okay, if pole is on the circle, unit circle, then it is a fixed signal, and if it is outside, then it is a growing signal. Right? Even we can identify the bounded and unbounded nature of the causal signal. If poles are outside the unit circle, then signal becomes unbounded. Such signal should be avoided, right? And if causal signals having poles inside the unit circle or on, the signal becomes bounded, right? So today we'll be discussing the system function of linear time invariant system, right? So the system function the system function of a linear time invariant system, right? So before this we have already seen how to obtain or analyze, how to obtain the output or how to analyze linear time invariant system, right? So the output, okay, the output of a relaxed LTI system to an input sequence x of n can be obtained by computing the convolution that we have seen. We can use convolution, or you can use the, or you can obtain the total solution of the given difference equation to identify the response of the given LTI system, right? So those two methodologies we have seen. In case of FIR system, we can go with the convolution, okay, because it has the finite impulse response. But when the system is IR system, that means if it is having infinite impulse response, then identifying the response of system by convolution becomes impossible, right? So in that case we can use the difference equation. We can solve that difference equation where we are identifying zero input response, zero state response, and clubbing those two responses, we can identify the total response of the system. So we have seen all these topics in previous session, okay. So here we'll consider that the output of a relaxed LTI system to an input sequence x of n, right, can be obtained by computing convolution of x of n with the unit sample response of the system. So this can be given as y of n is equals to x of n convolved with h of n, right? So this is nothing but the convolution of x of n with impulse response h of n, okay, or unit samples response h of n. We have seen this h of n is nothing but the response of system when you are applying input del of n to the system, right? So if you are giving this unit sample as an input to the given discrete time system, then its response, that system's response will be indicated by the h of n, okay, that is nothing but the impulse response, right? And this del of n, we already know that del of n is equals to 1 for n is equals to 0, and it is 0 otherwise. So it is one of the elementary discrete time signal, okay. And the response of an LTI system to the input x of n can be determined by using or by convolving this input with the impulse response, okay, by using convolution summation, right? And in Z transform we have seen the convolution property, okay. So as per convolution property of Z transform, This convolution in Z domain will be the multiplication of respective Z transform of X of n and H of n, right? So in Z domain, this Y of n will be Y of Z, and this convolution becomes multiplication, right? Multiplication of Z transform of X of n. So Z transform of X of n can be indicated by X of Z multiplied by the Z transform of H of n. So H of n Z transform can be indicated as H of Z. Okay. So X of Z multiplied by H of Z will be in Z domain. We have discussed it in the convolution property of Z transform, where we have seen what we have seen in convolution property. If x1 of n has the Z transform capital X1 of Z, and this x2 of n has the Z transform capital X2 of Z, right? Then this x1 of n convolved with x2 of n, right, as the Z transform in Z domain, it will be simply multiplication of x1 of Z multiplied by x2 of Z. Okay, so this thing we have seen. So in this case, when we are identifying the response of the system using convolution summation, in place of x1 of n we have x of n, and in place of x2 of n we have h of n. So their respective Z transform will be x of Z and h of Z, right? So we are simply multiplying it in Z term, right? So here we can say that y of Z is the Z transform of y of n, right? It is y of Z is the Z transform of output sequence y of n. Similarly, this x of Z is the Z transform of input sequence x of n, and h of Z is the Z transform of impulse response h of n, right? So depending on this equation, that is y of Z is equals to what we have, x of Z multiplied by h of Z, we can identify the system function. So system function is indicated by h of Z, so h of Z will be y of Z upon x of Z. Okay, so this h of Z indicates the system characteristics function. Okay, right? So this h of Z is also called as what? Simply system function. Okay, and h of Z, as we indicated here, h of Z is nothing but the Z transform of h of n. So that means the equation for h of Z will be summation n is equals to minus infinity to infinity. The formula for Z transform is summation n is equals to minus infinity to infinity x of n into z to the power minus n. But in place of x of n, we are identifying the Z transform of h of n. So h of n multiplied by z to the power minus n. So this is nothing but the Z transform of h of n, indicated as capital H of Z, and this h of Z is called as what? System function, right? So h of Z represents Z domain characterization of a system, right? So this h of Z indicates the Z domain behavior of the system or Z domain characterization of the system, while h of n, that is impulse response, indicates the time domain behavior of the system. Okay, time domain characterization of the system. So here h of Z indicates Z domain characterization of system, while h of n indicates time domain behavior or characterization of system, right? So here this transform, okay, the transformation h of Z, okay, is this h of Z is called the system function. It's called as the system function. Okay, so This is when we are identifying the response of system by using convolution summation, right? But in case of FIR system, we can use convolution summation. But if system is IR system, then we cannot use convolution summation to identify the response of the system, right? So by using convolution summation, to this convolution summation, we applied the convolution property. As per convolution property, this convolution will be multiplication in Z domain. So it will be x of z multiplied by h of z. Here this y of z is nothing but the z transform of y of n, and x of z is the z transform of input signal x of n, h of z is the z transform of impulse response h of n, right? And using this equation, y of z is equal to x of z multiplied by h of z, we can identify the system function as h of z is equal to y of z upon x of z. H of z indicates the Z domain characterization of system, while H of n indicates the time domain behavior or characterization of the system. And this H of z will be called as what? System function. But when the system is an IR system, so the response of such system can be indicated by the difference equation. So we already seen the generalized form of difference equation, right? How we are indicated is indicated that difference equation, generalized form of the difference equation is indicated as y of n is equals to summation k is equals to, so basically it is minus, okay, minus k is equals to 1 to n a k y of n minus k plus summation k is equals to 0 to m bk x of n minus k. We already seen this generalized form of the difference equation. This can be written as, if you are indicating the output terms on left hand side, and in compact form you can indicate as k is equals to 0 to n a k y of n minus k, right, is equals to summation k is equals to 0 to m bk x of n minus k, right. This y of n was inside the summation by transferring this term on the left hand side, so this minus become plus, so summation k is equals to 0 to n. Why 0 to n? Because y of n was shifted inside the summation, okay. So if you are substituting k is equals to 0 here, so it will be y of n minus 0. So as it is n minus 0, y of n minus 0, so it will be only y of n, right, and here it will be a0. So for this a0 should be 1, right. So if 0 is 1, so you can simply represent our equation by using this difference equation form, generalized form of the difference equation, right. So if you are considering this equation, and if you apply the time shifting property of Z transform, and if you take the Z transform of this complete equation by taking the Z transform and by applying time shifting property of Z transform, we get here the Z transform of y of n can be indicated as capital Y of Z, right, is equals to, the summation sign will be as it is, summation minus summation k is equals to 1 to n, ak is the constant, the Z transform of y of n minus k will be z to the power minus k capital Y of Z, right. Similarly, plus the summation k is equals to 0 to n, bk will be again constant, the Z transform of x of n minus k will be z to the power minus k capital X of Z, okay. This is as per what? Time shifting property, because as per time shifting property, if x of n has the Z transform x of Z, then the Z transform of x of n minus k will be what? Z to the power minus k X of Z, right. Let's written the property of Z transform, that is time shifting property. So the Z transform x of n minus k will be z to the power minus k x of z. So similarly y of n minus k will have the Z transform z to the power minus k y of z, and x of n minus k will have the Z transform z to the power minus k x of z. So again, if I'm using this equation, if I transfer these terms of y of z on left hand side, so I'll get y of z plus summation k is equals to 1 to n a k y of z, right? Multiplied by this z to the power minus k is this. So I'll write here z to the power minus k is equals to summation k is equals to 0 to n bk z to the power minus k x of z. Okay, so I'll rewrite that equation here. So what we have, y of z plus summation k is equals to z 1 to n 1 to n a k z to the power minus k y of z is equals to summation k is equals to 0 to n bk z to the power minus k x of z is the equation, right? So from here you can take this y of z common, and you can take this x of z outside summation, because the summation variable is k only, right? So if I'm taking y of z common, so I'll get in bracket 1 plus summation k is equals to 1 to n a k z to the power minus k is equals to x of z. I can take outside the summation. Okay, so k is equals to 0 to m bk z to the power minus k. Okay, so for the system function, as we have seen in the system function h of z is nothing but y of z upon x of z. So if I'm taking this y of z upon x of z, so I can integrate it as h of z. So h of z is equals to y of z upon x of z, and what it will be, so it will be simply y of z upon x of z will be summation k is equals to 0 to m, right, bk z to the power minus k whole upon this term, that is 1 plus summation k is equals to 1 to n ak ak z to the power minus k, right? So in rational Z transform, we are saying if there are numerator as well as denominator, if there is numerator as well as denominator, okay, in the Z transform, then by factorizing the numerator we can identify the zeros, right? And by factorizing the denominator we can identify the values of poles, right? So this function, this h of z, okay, so here this function is simply k is equals to 0 to n bk z to the power minus k, right, upon 1 plus summation k is equals to 1 to n ak z to the power minus k. So this indicates from the numerator we can identify the values of zeros, and from denominator we can identify the values of poles. But before that we have to avoid the negative powers of z. We have seen it in the rational z transform that were discussed in the previous sessions, right? So by taking or by avoiding the negative powers of z, and by factorizing these numerator and denominator, we can identify the values of zeros and poles. So this system is called as what? Pole zero system. Okay, because it comprises zeros as well as poles. Okay, so therefore this system is called as pole zero system, and pole zero system is generally an IIR system. Okay, so it is an IIR system, right? So LTI system described by a constant coefficient difference equation has rational system function. Okay, so its system function is rational because it comprises numerator as well as denominator. Okay, and if it comprises zeros as well as poles, then that system is referred as pole zero system, and it is an IIR system. Okay, so if I am considering only the numerator in this system, okay, so if just for example, this denominator is missing in this case, so this h of z will be, so if I'm considering this system function comprises only the numerator, okay, so it will be simply h of z is equals to summation k is equals to 0 to n bk, right? I'm writing simply the numerator bk z to the power minus k. Okay, so again, by avoiding these negative powers of z and factorizing this polynomial, I will get the roots of that polynomial. So those roots will indicate the values of zeros. Okay, so denominator is not there, right? So this system is called as what? All zero system. Okay, all zero system. So such system is an FIR system, that is finite impulse response system. Okay, so it is an FIR system, right? So h of z will contain capital M zeros, okay, whose values are determined by the system parameters, that those are nothing but the constant coefficient bk, and mth order pole at origin may be there, right? Basically, these systems are also referred as what? All zero system. Okay. So such system has a finite duration impulse response, and it is called as FIR, or moving average system. Okay. And second, if we are considering this numerator is not there, right? Correct. And if we are considering that the uh, remaining values are not present here, right? Only the denominator is present. So in that case, you can indicate this system function h of z, right? Simply some constant in numerator there, or you can consider it as 1, or you can consider it as b0, okay, simply. And the denominator value are present here, right? So it is 1 plus summation k is equals to 1 to and ak z to the power minus k. So in this case, zeros are not there, okay, only poles are there. Again, by avoiding the negative powers from denominator and by factorizing this denominator, we can identify the roots of this polynomial. Okay, so again, you will get the values of poles from the denominator. So such system is called as pole all pole system, right? And again, it is an RIR system, that is infinite impulse response system, because poles are nothing but the values of z, where x of z is infinity, right? So therefore it is an IIR system, that is infinite impulse response system. Okay, so what we have seen in this section, we have seen the system function of a linear time invariant system. So this is system function is denoted by h of z. Okay, so the system function of an LTI system can be denoted by h of z, and as we have seen, the behavior or analysis or response of LTI system can be identified by using convolution summation or by using difference equation. So we have considered the first condition of convolution summation. From convolution summation, by taking its z transform, we identified the system function, right? Similarly, by considering the difference equation and by taking the z transform of that difference equation, again we identified the system function h of z. But this h of z comprises zeros as well as poles, so such system is called as what? Pole zero system, and it is an IR system. But if you are considering only zero system, okay, only numerator has been considered, so such system is called as what? All zero system, and it is called as what? FIR system, or it is an FIR system. But if it comprises only poles, so such system is called as what? All pole system, and it is an IR system. Okay, so in next session we'll try to determine the system function and unit sample response by obtaining these system function of the given input output equation or the difference equation. So we'll be provided with one difference equation we'll take the Z transform of the difference equation. By taking its Z transform, we'll try to identify the system function, and by taking the inverse Z transform of system function, we can obtain the impulse response, that is nothing but h of n. So initially we will obtain h of z using difference equation. From h of z, by taking inverse z transform, we will get the value h of n. Okay, that example we'll discuss in the next session. So thank you for joining this session.